And then I will, let me see. I'm going to mute all of you, all right? So if you want to speak up, just unmute yourself and then talk to me. So let me mute you all. All right, so I think we are all ready to start. So this is the third lecture on the optics part. And before starting the lecture, I like to remind you that the week for Tuesday, next week Tuesday is the Chinese New Year holiday. Therefore, we have the mega class on the Thursday, okay, starting at the same time, 5:30 p.m. And then please use the same the Zoom link. So I will see you in the next year, all right, for the week for summary lecture. Now we finally enter the wave optics, and our first the topic is going to be the interferences. Okay, so interference, and then under this week 3, you're supposed to self-study those topics, the wave properties, and then the interferences and the Huygens principle, and then the double slit experiment and the interference by a thin film as examples of the interference, all right? So wave nature of the of light. In the last 2 weeks, we portrait the wave as a line. Yeah, so I introduced a lot of lines with the arrow to indicate the direction of the light flow, and also we use the geometry optics to determine the image formation, and also to determine whether those images are upright or virtual. And however, there are some phenomena that we cannot interpret with the ray picture. Therefore, that's why we introduce the wave, all right, the wave optics to explain, for instance, those interference appearing on the thin, the soap bubble. Once we get used to this wave optics, we complete the wave optics, then in the quantum optics or the quantum physics, so you will be introduced the photons. Okay, so we will then relate the light to the photons, but for now, we're in the week 3 and the week 4, we will use a wave to interpret the light properties. So we have the starting point is to draw some wave. Yeah, so I'm going to draw some diagram in my paper. So let me switch the screen, just 1 second. Yeah. Okay. I'm going to draw a wave, all right? So along this x-axis, this is the distance, okay? So we define this axis in a space. And then in the space, I will draw a wave. Okay, oscillating like this. And then I can say that the wave is the flow into this direction to the right, all right? And of course, you can determine the amplitude or magnitude of your wave oscillating from the maximum value to the minimum value. But also, you can define the phase, yeah, the phase of this the wave like this, yeah. So what's the phase of this point, and what's the point? The way you can define the phases along those waves. Now, let me pick up this point. Right, and then this point is measured length L from the origin, and I want to determine the phase at this point L. How can you do that? We learned this, the phase at any given point along the wave can be determined as, so we want to find the phase at the distance over L. This is going to be 2 pi over lambda times the traveling distance over L. All right, so maybe it's, well, you tend to memorize this way, and it's also easy to memorize. But let me just explain to you why we have this. So this 2 pi comes from one complete oscillation. All right, so when the light, the wave, complete one cycle of the oscillation, the change of this phase is 2 pi, isn't it? So after this first oscillation, it moves to the second oscillation, and in the second oscillation also it completed the cycle within 2 pi, okay, with the 2 pi over phase shift. So 2 pi is the maximum phase change over the one complete cycle. All right, so very straightforward. Then what about this lambda then? Lambda is a wavelength. We call it wavelength, all right? So wavelength is defined in this wave. So I'm going to say that the wave is defined from the start of the oscillation to the end of the oscillation. Okay, so one oscillation complete between these 2 points. Therefore, my wavelength is going to, or the distance or the length of this one oscillation is going to be defined as a wavelength. Now you can see that this wavelength is related to the 2 pi. Okay, whenever you have 2 pi of phase shift, then you are going to have one wavelength. Okay, so within one wavelength, you will have one complete cycle. That's how we define the phase at any given point along the wavelength. 2 pi over lambda times the traveling distance is that. All right, because we know that there is always the same oscillations along the wave. Now, I'm going to draw another wave. All right, so let me draw another wave. Okay, so my starting point is now shifted to here. In other words, I can define my origin at the intersection point, and again, my x-axis is a space. All right. Now my the wave oscillate from this point as this. Right. Now I want to find the phase at this point of the wave 1. So I'm going to say this is length 1, okay, in the first wave. And its corresponding distance for this wave 2 is going to be at this point. And then I'm going to say that the distance of this corresponding length is going to be L2. Now, well, we will just follow the same definition. The phase for those 2 waves at the point L1 and the L2 as, let me write those phases in a new paper. Yeah, we are learning out of the phase. So here, my phase 1. Distance of L1 is going to be 2 pi over lambda times L1. All right. And then what about our phase 2 from the wave 2? Well, this can be defined as at L2, 2 pi over lambda times L2. All right. Now we know that this L1 from this diagram, this L1 is 3/4 of the full wavelength. Yeah, 3/4 of the full wavelength. So this L1 is 3/4 of the full wavelength. So I will continue this writing as 2 pi lambda times 3/4 one wavelength. All right. And then what about this L2? When you look at this diagram, our L2 is 1/4 of the full wavelength. Yeah, 1/4 of the full wavelength. Therefore, sorry, just 1 second. Sorry about that. So let me continue. So this L2 is a quarter of the full wavelength. Therefore, my L2 is going to be changed to 2 pi lambda times 1 over 4 lambda. So our interest is to find the phase difference. So my phase difference is then delta pi is going to be pi 2 minus pi 1, which becomes 2 pi over lambda L2 minus L1. Okay, so this is 2 pi over lambda 3/4 wavelengths minus 1/4 wavelengths. Now you see the lambda go away, and then we will have pi times 1 over 2 pi 2, yeah, so let me write, okay, what's writing this, okay, so 2 pi over 2 over 4, yes, then this becomes pi, yeah. So now we see that the phase difference over those two waves, okay, at those points becomes pi. In other words, it becomes pi, yeah. In other words, those two waves are out of the phase. So I go back to this diagram, those two waves. Indeed, those two waves are out of phase. So if we combine those two waves, the resultant wave is going to be just flat, okay, because they interfere destructively. All right. So I want to go back to this equation again. So our working again. Now we see that if the phase difference becomes pi, then we have out of phase, and then it becomes the destructive interference. All right. So that's one nice conclusion. And then I also like to highlight this L2 minus L1. So L2 minus L1 is actually the difference of the traveling distances of the two waves. Yeah. So wave 1 travel up to L1, point L1, and the wave 2 travel to the distance of the L2. So this L2 minus L1 is actually the optical path length difference of those two waves. All right. And then from our calculation, what is this? This is 1 over 2 lambda, isn't it? Now, I can relate this destructive interference phase to the optical path length difference. You can now see that whenever our optical path length difference becomes half lambda, or 3 over 2 lambda, 5 over 2 lambda, and any integer number plus a half lambda, then we will have destructive interference. Okay, and of course our m is any integer number starting from 0. So m can be 0, 1, 2, 3, so on and so forth. When our optical path length becomes a full wavelength, like lambda, 2 lambda, 3 lambda, or in other words, any integer number times the wavelength, then we will have constructive interference. All right, so this is a very important conclusion. So when you compare two waves, if they meet at half wavelengths, then they will result in the destructive interference. However, if the two waves meet at the wavelengths, one full wavelength, or any integer number of the wavelengths, then they will interfere constructively. All right. Now let me go back to the lecture note. All right. So I just explained about the phases and how we can find the phase, and I just related the wavelengths to the optical path length. All right. So we have the optical path length in the definition. We read the definition of this wavelength. Now our upper medium has a refractive index N1, but this refractive index is smaller than the refractive index of our second medium. In other words, the light travel faster in the upper medium because the index is low. Yeah, we learned about this in the first week. But what do you mean? What do you mean by traveling faster in terms of the wave? Now this diagram will illustrate where in the upper medium with the lower refractive index, one oscillation of the wave can make this much of distance, while on the other hand, in the second medium, one oscillation only make this much of this the traveling distance. So our traveling distance, all right, our traveling distance over the same amount of the time is longer in the upper medium because it travels faster. So in one oscillation, it can cover longer wavelength, or longer distance. And then this is now explained in terms of the wavelength, all right? Now, obviously, the optical path length of the second medium is longer because N2 is large. Therefore, we can conclude that optical path length is longer in the second medium, and the wavelength is shorter in the second medium. So it oscillates, okay? It oscillates within the shorter distance. All right, so now we have some idea how to relate the wavelengths to the optical path length. That's good. And where this wave optics actually give us some idea about the new wave front. So where this is explained under this Huygens principle, this principle states that if we are given any arbitrary number of the point sources, then they will emit their own wave front. Yeah. And then where we just trace those the new wave front from each of the point sources, and at a given the time you just freeze the propagation, then you just connect those wave front from each of the light sources. Then you connect the wave front, which now define the new wave front from the light source. All right, so this looks very obvious, and then seems not much. It seems to not have much the meaning. But then this Huygens principle actually explain the refraction and the reflection. And then for the refraction, it's already explained in the LAMS videos. So please go and watch how we can derive this Snell's law with the Huygens principle, okay, or using the wave optics. Now I think we can have a quick the quizzes. All right. So can you please scan this QR code so we can have the question live polling session. So I'm going to also switch my screen to the live poll session. Okay. So, well, please scan this QR code to join this polling. I will start the first question. Sorry. Yeah, the two waves shown are like this. And then what do you think is the phase difference? You can start the vote now. All right. I am going to close the board in 5, 4, 3, 2, 1. Okay, the correct answer is 2, as most of us believe. Okay, so I come back to those questions and the solutions later. So let me move on to the next question. Two light sources emit wavelengths of the 1 meter wavelength, which are in phase initially, and then they travel. All right, and the wave 1 travel 2 meters to reach the point, and the wave 2 travel 3 meters. When the waves meet, they are out of phase, but not 180 or in path length difference of a quarter wavelength or in phase. So this wave has 1 meter of the wavelength, and then they travel 2 meters and 3 meters. All right. So when they meet, will they interfere destructively or constructively? All right. I'm going to close the board in 5, 4, 3, 2, 1. The correct answer is in phase. All right. So I will come back to this question again later. But let me move on to the next question. Okay. Sorry. Well, that's it for the first part of the UCLEC questions. I will come back to the rest of the questions later. Okay. So before then, let me go back to the lecture note. All right. So this is our first question. The two waves shown are like these. And then if we want to compare the phase, well, you just select one point, okay, over the wave. And then in the, and then you just look at the second wave at the same, the traveling distance point or the same X point. And then you see that they are 90 degrees of the out of phase, 90 degrees of the phase difference. Therefore, the correct answer is the 90 degrees of phase difference. You can also compare the wavelength from here to here. It's 1/4 of the wavelength difference. All right, so you can actually relate the wavelength to the phase, which is going to be 90 degrees or 1/4 of the wavelength. Now the two the sources emit wavelengths of 1 meter wavelengths, which are in phase initially, and then two waves from these sources emit a distant point, and then wave one cover 2 meters. 2 meter means 2 cycles of the 1 wavelength, and the wave 2 travels 3 meters, which means it oscillates 3 times of the wavelength. Therefore, when they meet, they are still in phase, and then they will interfere constructively. Okay, I hope those answers clear your doubt. Now let me move on to the next topic. So we now have some understanding about the wave properties, and then I already explained to you that those two waves can interfere if they are coherent. In other words, their wavelengths are fixed. So two waves can interfere destructively or constructively, and our very first example of this interference is a double slit interference. Okay. I will briefly talk about this double slit interference because this is the very first time I introduce. So let me use my second camera to draw some diagram. Just 1 second. All right. Something goes wrong. Just 1 second. I will make the new connection. Okay, so I'm going to draw some the diagram for the double slit interference, all right? Okay. So we have two slits on the left-hand side, and then we have a screen on our right-hand side. And I can define a line that connects those two vertical lines, but it cut across the center of the two slits. And then, oh well, let me assume that the wave from the first slit will travel and then reach to the point of P here. And then the wave from the second slit also travel and then reach the point on the screen at the same point. And then I'm going to say that while the traveling distance for the first wave is R1, and then traveling distance for the second wave is R2. All right. I previously explained to you that we can determine the interference or destructive or constructive interference depending on the optical path length difference. Yeah, if the optical path length difference amounts to m lambda, then we are going to have the constructive interference. So when it comes to the interference, the first thing we need to do is to define the optical path length difference. The optical path length difference in the double slit is going to be defined as d times sine angle theta. So what is d? The d is the distance of the two slits. And then angle theta is determined here. So I'm going to use this horizontal line as a base of the triangle. And then I'm going to introduce another line from this center to the point P. All right. Then you can see we can find a right angle triangle, and then the angle theta is determined here. Okay. And so well, this is the optical path length, d sine theta, and then we know that if this if the optical path length becomes any m lambda, then we will have bright fringe. Okay, in other words, the constructive interference, and then when this optical path length difference becomes m plus half lambda, then we will have dark fringes. All right, and then I'm going to, for this double slit, I'm going to put the plus minus signs, which indicate the fringes appearing above these central lines, and then a fringe appearing below the central lines. So I can draw the fringes like this, fringe pattern like this. We have a bright fringe in the center, and then dark fringe, and then bright fringe again, dark fringe, bright, dark, bright, dark. And then we can have the symmetric pattern below this this center line. So bright, dark, bright, dark, bright, dark, bright, dark. All right. So there we have the alternating dark, bright fringes. Now, well, our m value can be any integer number starting from 0, yeah, 0, 1, 2, so on and so forth. So when I go back to this diagram, I can define, okay, these integer numbers. So in the center, obviously our m equals 0, which means our optical path length difference is going to be 0. And then the next bright fringe will have m equals 1, and then our m value will increase, okay, to the when we move to the adjacent bright fringes. And then where below this central line, we will have m equals -1, m equals -2, -3, so on and so forth. All right. Now, what about these dark fringes then? Of course, we need to look at the total first. Okay, so here our m becomes +1/2, and then the next dark fringes, our m value is going to be 3/2, and then our next m is going to be 5/2, yeah, 5/2. And then when we move to the below the fringes below this center line, then our m, of course, is going to be -1 over 2, and then -3 over 2, so on and so forth. So we can determine these bright fringes and the darker fringes above the central line and below the central line, and then the size will determine those locations, all right? Now, when it comes to this double slit or even for the single slit, we very often ask to find the location of this dark fringe or bright fringe, all right? So let me have a look at this point P. The point P, which is the third dark fringe, is located, okay, from this distance, from the central line. And then I'm going to say that this is y bright. Okay, the distance from the center line to the bright fringe. Oops, sorry. So the camera was just off. So let me continue. What we want to do is where we want to find the height or the distance of this point P from the center line. All right. In order to find this the point P, or the distance from the bright fringe from the center, we will use this big triangle. All right, and then where with the distance between this slit and the screen of L, my y bright, the distance of the point P from the center, so y bright is going to be, this is actually the height of this big triangle, isn't it? Therefore, this becomes L times tangent angle theta. And if this distance is very large compared to this slit separation, then this angle becomes very small. Then we can now introduce a small angle approximation, which will go like L times sine angle theta. Okay, so this sine theta is very familiar with us because this is the part of this optical path length difference. Then we substitute this into this sine theta. Then we will have L times plus minus m lambda over T. We can determine the bright fringes using this equation from m equals 0 to 3 and then all the way until it hits this maximum value. And then of course you can derive this location of dark fringes using the same procedure. All right. Now let me go back to the lecture note. All right. So I just explained that this our optical path length difference is defined as a d sine theta, and then the actual derivation of this optical path length difference is given in the last video. So please go and watch the video. And whenever the optical path length difference amount to the integer number of the wavelengths, we will have the bright fringe. If we have m plus half wavelengths, then it will result in the dark fringe. And I also just show you that how we can find the location of the bright fringes using this big triangle, and also you can derive the location of dark fringes following the same the procedure. Now I like to talk about one of the tutorial question this week. So where we are given this double slit experiments, however, with this double slit experiment, however, in one of the slit, the glass plate is inserted, all right? So because of as a consequences, each bright fringe moving to the location of the adjacent bright fringe, all right? With that, we want to determine the minimum thickness of the glass plate. Right. So, well, I will just to show you how we can approach the question, and then all the workings will be introduced by your tutor. Okay, so let me just briefly tell you how we should approach this kind of question. I'm going to use my paper, I will draw some diagram again. All right. So let me draw the double slit diagram here. And then, well, the two wave travel and then hit at the point P, all right, on the screen. And without the glass plate, they generate this bright fringe like this. Okay, now a glass plate is inserted to one of these slit. As a result, this bright fringe now move to the adjacent bright fringes like this. Okay. Then what's the optical path length, or what's the thickness of this glass? What's the thickness of this glass? Well, this is again the interference, which means our starting point is going to be the setting the optical path length difference. So our optical path length difference, well, without the glass plate in the double slit experiment, is always the sine theta, isn't it? And then we are interested in the bright fringes, therefore I will put plus minus m lambda. And then I may just ignore this plus minus sign because those plus minus sign, just 1 second, while my camera freeze again. Yeah, sorry. So when I delete this, I ignore this plus minus sign because plus minus sign only give us information whether it appear above the center line or below the center line. So I just ignore because I know that I know where they actually appear. So I will just put m lambda. All right. Now with this insertion of this glass plate, our optical path length must change. Yeah, must be changed because of this insertion of the glass plate. Therefore, my new optical path length is going to be d sine theta, the original optical path length difference, plus something else. Yeah, plus something else, which results in shift of the bright fringe to the next bright fringe. In other words, this optical path length still results in the bright fringe. Okay, so we still have the same bright fringe with the insertion of the glass, but they just shift one step. In other words, I can set the equation like this. Well, it's going to be the same bright fringe, but it shifts to the next point. So m plus 1 lambda. All right. Now, what you are going to do is you will combine those two equations to determine the new optical path length difference introduced by this glass plate. And then from there, you can find the thickness of the glass. All right. Now, well, here, we assume that this bright fringe moved to the adjacent next bright fringe. What about this? If the bright fringe moved to the dark fringe, okay, the bright fringe moved to the dark fringe, then what should be our new optical path length difference? Our new optical path length difference is going to be half lambda, isn't it? So it moves from the bright fringe to the dark fringe. Therefore, the new optical path length difference is going to be m plus half lambda. And then again, you will combine those two equations to determine this additional path length introduced by this glass plate, and then you will find the thickness. All right. Now I will go back to this lecture note. All right. So I hope now you know how to approach this question. Our next example of the interference is the interference appearing in the film. All right. So again, this is interference. So what you have to do is to set the optical path length difference. So we just need to define the optical path length difference. So here, let's have a look at this diagram. In this diagram, we can see that there is incident light which is reflected by the first interface. and then reflected by the second interface. So when those two waves come out from this the film, they will interfere. All right, depending on the optical path length difference, they can interfere constructively or they can interfere destructively. Then how can we define this optical path length difference? Well, if you examine those two diagrams, the only difference of this wave 1 and the wave 2's path happens inside this oil. In other words, we have additional round trip for the second wave. Therefore, our optical path length difference is going to be 2 times thickness T, the thickness of the oil. Yeah. So this is the thickness of the oil. So we have a round trip. Therefore, we should multiply 2 to this thickness times refractive index of the oil, because we need to take into account this optical path length rather than the geometric length. So these 2Tn or 2Tn is our optical path length difference in the thin film interference. And if this becomes m lambda, then we will have constructive interference. And if they have m plus half lambda, if they have m plus a half lambda, then we will have destructive interference. Well, it's always the same. Yeah, in phase constructive interference, out of phase destructive interference. But when it comes to this thin film interference, there is one additional thing you need to be careful. All right. When the wave is reflected by a material with a higher refractive index, then the phase just flipped. Okay, so phase gets inverted when it's reflected, okay, on the reflection. On the other hand, if the wave is reflected by lower refractive index material, then the phase will remain the same upon the reflection. So we don't need to worry about this phase shift. So you have to check the reflection. Okay, if the reflection is done by higher refractive index, then we have to take into account this pi phase shift. If the reflection is done by lower refractive index material, then there is no change. All right. Now, we have one example in our lecture note. So, I think this is a very good lecture note, a very good example. Therefore, I like to go through this interference in my handwriting diagram. So, just 1 second. Let me switch the camera. I'm going to share my camera screen. Okay. Yeah, it's up. I'm going to draw 2 horizontal lines which represent the interface between the air and the film. So above this, the horizontal line is air, and then below we have a film with the refractive index over n, and then where the film is floating in the air, in other words, below the film is also air. All right. Now we have an incident light, which is reflect into this air to the film, and then it will bounce back and then coming out, okay, from the film. And then another wave is immediately reflected by the first interface. So we have a wave 1 and a wave 2. Well, if we want to determine the bright fringe, we know that our optical path length difference must be m lambda. Then we are going to have the constructive interference in the bright fringe. Well, when it comes to this thin film interference, again, we need to be careful. Yeah, we have to check the reflection or the phase shift by the reflection. So let's first have a look at this first wave. This first wave is reflected by the film whose index is larger than the air. Therefore, the phase upon reflection has pi phase shift. What about the second wave? The second wave is reflected by air, and the air's refractive index is lower than the film. Therefore, the phase shift by this second reflection is 0. There is no phase shift. Then our phase difference between those two waves by the reflection is going to be pi minus 0, which is pi. So, well, without considering this optical path length difference, we know that those two waves are already have the pi phase shift, where they have the pi phase difference. So pi phase difference. So this pi phase difference is corresponding to half wavelength in terms of the length. Therefore, I will take into account of this half wavelength into our equation. In other words, our optical path length is going to be m plus half lambda for the bright fringe. Okay, similarly, you will have m lambda for the dark fringe. Okay, so now we see that some different the equation for the bright and the dark fringe because of the reflection. Okay, now let me go back to the lecture note. Okay, so well, for the dark fringe, our optical path length difference becomes m lambda, and then our the bright fringes, our optical path length difference becomes m plus a half lambda. All right, because there is already the pi of the phase difference between those two waves upon the reflection. All right. Now I have a question in the chat room, so let me read the question. Does that mean the angle of refraction is negligible here for thin film? Angle of refraction is negligible here for thin film. This is a very good question. All right, so in our thin film interference, we always assume that this incidence is normal incidence. In other words, our incident light should be drawn like this by right. So the incident light will make 90 degrees to the with the interface. So this is a normal incidence, and then our reflection by the second the thin film second interface will also come out as this, like the vertical straight line. All right. Therefore, our optical path length difference is going to be 2 times this, just this round trip, yeah? So 2t times the refractive index of the thin film. All right. I have another question. What do you mean by no phase change? Is it with respect to the ray 1? Okay, let me go through this again. So the ray 1 or the wave 1 is reflected by the film. Okay. So film has a higher refractive index than the air. Therefore, upon this reflection, the wave experiences pi phase shift. On the other hand, this wave 2 is reflected by the air. So air's index is obviously smaller than the film. Therefore, there is no phase change by this reflection. Then wave 2 will come out with no phase change, okay, by the reflection. Therefore, those two waves, the phase difference between those two waves is already 180 degrees. And then we need to take into account this 180 degrees phase change in your optical path length equation. Okay, I will move on to the next question. Is there any phase change due to the refraction? Well, we don't have a phase change by the refraction, but we have the phase change by the traveling. So when I started this the lecture, I drew this wave, yeah, sinusoidal wave. I drew this sinusoidal wave, and then this wave traveling to this direction. All right. And well, along the way, but you can easily see that where those the face along the wave are not constant, they all change. Therefore, when wave traveling in the space, we assume that the phase also change. And then for the refraction, okay, for the refraction, like the Snell's law, we don't really need to worry about this change of this the phase. But what we need to do is we will calculate the optical path length, which is related to the phase itself. Okay, so that's why we focus on the optical path length. I will move on to the next question. Yeah. How about the image formed? Which values of M to use? Okay, so about this question is not very clear to me. So in the image formation in our previous lecture, the M, okay, so the large M represented the magnification, but when it comes to this this interference, this small m is just integer number starting from the 0. It gives us the order of the interference. Okay, so 0, 1, 2, 3, or 4. All right. Hopefully that's clear. Let me move on to the next question. So if B is a medium optically denser than medium A, then there will be a phase change. Yeah. So if the light, if light is reflected by denser medium, then it will always accompany the phase change, pi over the phase change. Let me go to the next question. Can you please repeat why the dark and the bright equation is now changes based on your drawing? I think I already answered to this question. If you're still not clear, can you please come to me after the lecture, all right? And then I have one more question. This situation only applies to thin film, meaning the thickness is small enough to have a reflection, right? What if the thin film is replaced by other such as lenses? All right. This is a good question. So interference requires the coherency of the two waves, and then the coherency can be very well maintained if the optical path length difference is very, very small. If you already attempt the tutorial questions of this week, then you may notice that the calculated film thickness is in the order of 100 nanometers. Okay, so which is very, very thin. All right. Therefore, where in our interference, where we look at a very thin layer rather than the thick layer like a lens. All right. So in some cases, you may see some interference pattern or the rainbow color from the lens surface. That rainbow color was the rainbow colors are generated by the interference again, because usually the high-end lenses come with anti-reflection coatings. So there are multiple layers of the thin films coated on top of this lens surface, and then the rainbow colors are actually generated by the thin films coated on the lens surface. So yes, well, so the lens itself is not going to generate this the thin film interference, but the anti-reflection coatings on the lens surface will generate the interference pattern. All right. I will now then move on to the next topic. Well, so this slide will give you some idea how we can shift or convert these constructive and destructive conditions, okay, by applying additional layer, and then I believe you can actually derive those two equations, all right? And then if this is still a bit confusing, I hope you can watch the animation, the animated video in the LAMS in the NTU Learn. This animation is actually very nicely explain how we can visualize how we can have the destructive interference and then constructive interference, which involves this reflection phase shift by the reflection. So please go and watch this animated video, which actually help you understand from the visualization. Now, well, this table actually summarizes the interference conditions. So when we consider Young's double slits, then optical path length difference is d times sine theta, and our bright fringe always appear when the d sine theta equals m lambda, and the dark fringe will happen when d sine theta equals m plus half lambda. Now, when we move on to this thin film, then our optical path length difference is going to be 2nt, all right? Now, this 2nt can be can generate the bright fringe with m plus half lambda if there is pi phase change by the reflection, okay? If there is no change or the change of 2 pi of the phase change by the reflection, then our optical path length difference becomes again m lambda for the bright fringe and m plus half lambda for the dark fringe. Yeah? You do not need to memorize this, but well, I hope this actually somehow help you to understand or confirm your understanding. All right. Now, I like to show you this tutorial question. A beam of 500 nanometer light passes through two closely spaced glass plates. For what minimum non-zero value of the plate separation D, all right, is the transmitted light bright? So, well, let's assume that we have two glass plates, and then we, well, see these two glass plates from this direction, okay? And then you know that this small d, which is the gap between those two glass plate will determine the optical path length difference of those two emerging waves. So our optical path length difference is going to be 2 times d times the refractive index, well, which is going to be 1 because this is air, all right? So my intention here is not going to, well, solve this question, but I want to ask you something. Now let's assume that where you set the equation for the bright fringe, yeah, because of where the question asks us to find the bright fringe condition. So you will set the equation without a big problem, yeah, for the bright fringe, yeah. Now you determine this the separation at D, all right. What would happen if you increase this D? What do you think? Use set this distance for the first bright fringe, yeah? And then you increase this distance. So then what would happen? What would you see while increasing this distance? Any idea? We are going to increase this separation, okay? This air gap. And then what would happen? Are you going to keep seeing the bright fringe, or you are going to see dark fringe, or what would happen? I have a very good answer. First get dark fringe and then get bright periodically. What do you think? Do you think this is a good answer? Well, I'm going to write two equations here. Yeah? So let's say we're m lambda and then m plus half lambda. All right. And we know that, well, at the given, well, when you solve this question, you will have this gap, well, which is something, yeah, some number, and then this satisfies this equation. Let's say, well, this equation, yeah, for the bright fringe. Now you are going to increase this d, then what would happen? your equation to the end will satisfy the dark fringe condition. And then if we keep increasing this distance, then we will reach to, this will result in the second order of the bright fringe, which with the m value of 2. Okay, and then if we keep increasing this distance, then we will have dark fringe, bright fringe, and dark fringe, bright fringe, where we will have these alternating dark, bright fringes, okay, by increasing the distance of D. All right, and then this understanding is very important to appreciate this Newton's ring. Here in this Newton's ring, I will play this animation, just 1 second. All right, so here in this Newton's ring, we can draw two waves, okay, reflected by this curved interface, and then reflected by this flat interface. And then, well, depending on their optical path length difference, we can have a constructive interference, or we can have destructive interference, yeah. And yeah, so we can have also destructive interference depending on the optical path length difference. What I like to highlight here is this: our thickness, okay, of the gap, our thickness of the gap, this T, that determines the optical path length. This thickness T is varying along the length. Okay, this thickness T is not a fixed value any longer. This T is actually changing over this distance. In other words, we are going to have alternating dark fringe and then bright fringe because of the varying thickness. Okay, therefore, if you look at this Newton's ring from the top, then you are going to see this kind of alternating or concentric dark rings. All right, and then this is called Newton's ring. All right. Now, well, this is one of the tutorial questions again. Let me repeat this, the variation of the thickness. So here we are given this the diverging lens, and then where those two waves of the interference where that interfere already illustrated in this diagram. And those, where, as you can appreciate in this diagram, the optical path length difference of those two waves is determined in the gap, yeah? So inside this, between those two glass plates. Now, this thickness T changes over the length. In other words, our thickness is going to be maximum in the center, and then our thickness is a minimum on the edge. Okay, and then when you set the equation for the dark fringe, so in the question, we are interested in the dark fringes, okay, dark spot and then surrounded by dark rings. So we are interested in the dark fringes. So you are going to set the equation for this, the destructive interference, and then where I can say where this is going to be 2 times T. Index is 1 because we look at this air gap. This becomes m lambda for the dark fringe. Okay, so where this becomes m lambda because we have some the phase shift by the reflection. Now, well, with this equation, we know that this m value can be any integer number starting from 0. Okay, 1, 0, 1, 2, so and so forth. Go back to this question. Well, it is given that we first have the dark spot in the center, okay, dark spot in the center, which is surrounded by 50 dark rings, and then the largest is at the outer edge of the lens. So we will have the 50th ring on the edge of this lens. Therefore, all together, we will have 51 dark fringes. One in the center, which is surrounded by 50 other dark rings. Yeah, so altogether 51 dark fringes. Then our maximum number, because all those dark fringes must satisfy this equation for the distortive interference, which means all these number, the number of the dark fringes will be assigned with a different m value. So because we have altogether 51 dark fringes, our maximum m value is going to be 50. Isn't it? Because it started from 0. So 0, 1, 2, 3, 4, all the way to the 50. Then, because our thickness is maximum in the center, therefore, according to the question, our m value in the center must be its a maximum value, because in the center, the thickness is the largest. And then on the edge, our thickness is 0, isn't it? So they are in contact, two glasses in contact. So thickness is 0. Therefore, in other words, our m value is 0. Does it make sense? So we are going to have 51 dark fringes on this Newton's ring, and then you now understand how to determine this thickness, okay, using the destructive interference condition. All right. Now I have a few questions in the chat room, so let me go through those questions. Okay, for the double slit, will the amount of the slit affect the formula we try to use? For example, instead of 2, we have a 3 slit. How do we approach it? This is a very good question. I will leave my answer, okay, to the next week, because in the next week we have a topic of the multiple slit. All right, so please wait. I will come back to this. I can answer to this question in the next week. So in the next question, I don't get what are constructive and destructive interference. So how do they apply on? Well, constructive interference means where they come out in a bright fringe, and then destructive interference means that they the two waves cancel each other. Therefore, there is no light coming out from the interference. So we see only the dark fringe. All right. So if this is still not very clear to you, please approach to me after the class. Let me move on to the next question. Why the light does not reflected by the top side of this upper glass? This is a better question. So, of course, there will be light reflected by this upper interface. That can happen. Then this will interfere some other light reflection while coming from this curved surface. And again, this is a question of the coherence. Those two waves can interfere, but the chance of the making a good interference is not very high, because the glass thickness is in a few millimeters or even in the centimeters. All right. Therefore, on the other hand, we are going to have a very strong interference from the reflections coming out from this gap, because the gap thickness is very, very small, in the 100 of a nanometer order. Therefore, the two waves are still in a good coherency, and then they can interfere strongly. All right. Let me move on to the next question. What happened to 2nt equals to m lambda? Why is the n not needed? Sorry. Well, so in my equation here, I ignored the n. So m must be there. You're right, m must be there. But this refractive index is 1, because we are looking at the air gap. So air's refractive index is 1. Therefore, I just simply ignore that. All right. Now I will move on to the next question. So two glass plates and a thread. So this is again another tutorial question. So let me try to explain to you, okay, how we should approach this. So two glass plates and a thread form an air wedge. So air wedge is formed here, and then most likely we will look at the two reflections around this air gap. In other words, first reflection come out, yeah, so reflected by this first interface between the air and the glass, and then second reflection will be illustrated as this, yeah, reflected by the second interface between the air and the glass. All right, so in that case, we can also appreciate now the optical path length difference is now determined inside this the air gap, and then this air gap thickness actually varies along the length. In other words, when we look at this air wedge from top, we should be able to see dark, bright of alternating patterns because the thickness varies. All right. Now, I think that's pretty much of covering this content. Then I have a few questions for you to answer. All right, so I'm going to switch to the Uclap question screen. Just 1 second. All right, let's start with this question. In double slit experiment, when the slit distance D increase, then what would happen to the interference pattern? So do you think that the interference pattern spread out or shrinks or stay the same or disappear? We are increasing the slit distance D. So what would happen? I'm going to close the board in 5, 4, 3, 2, 1. The correct answer is just string together. Okay, I will come back to those questions later. So let me move on to the next question. So in double slit experiment, what path difference have the waves from each slit travel to give a minimum at the indicated point position? So in other words, what would be the optical path length difference at this point? What should be the optical path length difference at this point? So this is a dark fringe, yeah? So what should be the optical path length difference? You can start the vote now. All right. I am going to close the vote in 5, 4, 3, 2, 1. Yeah, the correct answer is 5, more than 3 wavelengths. Okay, well, let me move on to the next question. So in a double slit experiment, will there be an infinite number of points on the viewing screen where constructive interference and the destructive interference occur, or only the finite number of the point? So infinite number or finite number? I give you a hint, please. Well, use this equation d sine theta equals m lambda. So do you think this integer number m can go infinity? I will close the board in 5, 4, 3, 2, 1. Okay, the correct answer is 2, the finite number. So I will move on to the next question. Interference pattern is seen from the two slits. Now cover one slit with glass, introducing a phase difference of 180 degrees. Then what would happen to the pattern? We introduce a glass plate here to one of the slit. All right, then what would happen to the interference pattern? So do you think the pattern will vanish or expand, shrink, or not change at all, or the bright dark fringe interchange? I will close the vote in 5, 4, 3, 2, 1. Okay, the correct answer is 3. Yeah, bright and dark fringes are interchanged. I have another question here. Well, green light has a wavelength over 500 nanometer in air, and then green light is reflected perpendicularly from a thin film with an index of refraction of 2, and then the film appears bright in the reflected light. How much additional thickness would make the film appear, dark? So we currently have the bright fringe, then how much the thickness you are going to add to make it to the dark fringe. So are you going to add 1 wavelength thickness, or half a wavelength thickness, or 1/4? Well, what would be the minimum thickness to convert the bright fringe to the dark fringe? I'm going to close the board in 5, 4, 3, 2, 1. The correct answer is 5. I will come back to this question later, right? Now, consider 2 identical microscope slides in air illuminated with a single wavelength laser. The slides are exactly parallel, and then the top side is moving slowly upward. Then what would happen to, so what do you expect? All black, all white, moving apart, or change from the black to the dark fringe to the bright fringe. So I'm going to close the board in 5, 4, 3, 2, 1. Right, the correct answer is 4. Okay, so alternately were all black and then all dark, all black and then all bright. Right, I think this is our last question. So consider 2 identical microscopic slides in air. All right, and then the bottom slide is now rotated over so that the glass wedge gets a bit smaller. Then what would happen? The space farther apart, or space close together, or no change at all. So the thickness now gets smaller. So then what would happen? Let me close the board in 5, 4, 3, 2, 1. The correct answer is 1, space further apart. Now I will go back to this lecture note, and I will give you some answers. Yeah. So the first question, so how to happen? Well, the correct answer is 3. They will shrink together. So if you remember this question, then we will see that we increase this distance of the slit. Okay, m lambda is fixed. In other words, our angle must reduce. Therefore, the overall pattern will shrink. All right. Now, this is our second question. What would be the optical path length difference at this point? Well, this largest peak is at the center with m value of 0, and our the first dark fringe happens with the optical path length difference of 1/2 lambda and 3/2 lambda, 5/2 lambda, and then therefore this must be the next dark fringe have the optical path length difference of 3 + 1/2 lambda. Yeah, therefore the correct answer is 5. Now, in double slit experiment, will there be any infinite number of points, okay, of the constructive and then destructive interference, or we are going to have a finite number? The correct answer is finite number, because in your optical path length difference, we have d sine theta, and then this angle, this sine theta cannot be any larger than 1. Okay, in other words, the maximum angle is 90 degrees. You cannot actually make any larger than 90 degrees. Therefore, there is a certain finite numbers of the interference pattern. Okay. Now, where in this double slit experiment, we introduce this glass plate, then what would happen to this interference pattern if this insertion of the glass plate induce the phase shift of 180 degrees or half wavelength of this optical path length difference? Well, this is a half wavelength, which means the dark fringe will move to the bright fringe, or bright fringe to move to the dark fringe. Therefore, the correct answer is 3. Yeah, bright and dark spots are interchanged. Now, this question might be a bit tricky, but let me try to explain it to you. So I'm going to use my the paper and I will draw some diagram. All right. So just 1 second. Yeah, I'm going to switch to my camera. All right. So let me just copy this diagram. So this is a film with the index of 2.0. Above we have air, and then below we have air. All right. Now our optical path length difference is determined inside this film thickness, and then I'm going to say that 2 times n times t. Okay. So currently we have a bright fringe. So where in order to determine this the bright fringe condition, we need to check this reflection or the phase shift by the reflection. Yeah, the first wave is reflected by the oil, therefore it accompanies pi phase shift. The second reflection is done by the air, therefore there is no phase shift. Therefore, the phase change by the two reflections is going to pi minus 0. So this is pi. This corresponds to half wavelength. So we need to factor in this into our equation. Yeah. So because firstly we have a dark fringe, so our equation will be m lambda for the dark fringe because we have a half wavelength of the phase difference already by the reflection. Yeah? So this will give us the dark fringe. Now we want to change it to this the bright fringe. So our new thickness, okay. So our new thickness will generate m plus half lambda of the optical path length difference. All right. So because we are interested to know the additional thickness added to the original thickness, therefore, we are interested in the delta t, which is t minus t prime minus t, and then this is lambda. This is going to be 1 over 2 lambda, 1 over 2 lambda divided by 2n. Okay, from when you combine those two equations, you have this, and then this becomes lambda over 4 times n. Okay, so wavelength is 500 nanometers, index is 2, therefore this becomes 62.5 nanometers. Okay, so the correct answer is 62.5 nanometers. Now I want to keep using my hand drawing to explain to you about the interference pattern from this air wedge. This is the air wedge with a thickness of t. All right, with this we can set the optical path length difference as 2n t equals m lambda. Okay, for instructive interference, the destructive interference or the constructive interference. For now, it's not my concern. Yeah, this optical path length difference must be m lambda. Okay, for destructive or the constructive. But so we are going to have a destructive or constructive interference with this condition. What we want to know is this. Now, we are going to make this thickness smaller. So let me draw the line like this. Okay, so this is our new thickness. Then what will happen to the interference pattern is going to increase or the spread apart or they shrink. All right. Now, so our second equation will be given as this. All right, with the smaller thickness. Now, let me go back to this first equation, and then let me try to visualize the actual interference pattern. So we are going to have some dark fringe here, all right, with 0 the thickness, and then we will have a second dark fringe somewhere here with something T, yeah. I'm going to say T2 for the second dark fringe. So we have a second dark fringe here. Now, well, when I compare those two equations, you will see that this m lambda, let's say where m lambda is always there, and then the thickness is the only variable in our diagram, isn't it? Therefore, if we reduce this thickness to the T prime, then this second dark fringe must, this second dark fringe should have this same thickness. In other words, with our new the L wedge, this thickness will only appear somewhere here. Okay, here we have the same. Here we have the same thickness of T2. Therefore, when we reduce this the overall thickness, our second dark fringe will appear here instead of this. Therefore, we can conclude that the interference pattern will spread out because this required thickness for the second dark fringe is only satisfied at this location. Therefore, it will spread out. All right. Now I will go back to the lecture note to show you the answers. So, well, question number 4. So, where we just conclude that the additional thickness must be 62.5 nanometers, and then yeah, well, these are the working. Yeah, the additional thickness must be the quarter of the wavelengths inside the film. Now, when we increase this gap, then well, we will see the alternating of the dark fringe and the bright fringes. And finally, when we reduce this overall thickness of the air gap, then well, the fringes will move apart. Yeah, they will spread out because the second dark fringe condition, for instance, only satisfied in the longer distance or longer position from the contact point. That's it for this week's summary lecture. So thank you for attending this lecture, and then we are going to have the last summary lecture in the next week after the Chinese New Year holidays. So I will see you next week Thursday. All right. Thank you. Bye.